Hi everybody. Well, I'm sorry I can't be there today. Thanks to Ms. Sidhu for coming in on short notice. There are a few things I'd like to show you just before you write the test. So this is not good TV. The lighting's bad, the sound's bad, everything's bad. But hopefully the content is good. Here we go. Here's the data booklet that you will have for the test. Everything you need will be provided on it. Here, let me just move that for a sec. Everything you need will be provided on it. The familiar periodic table. Draw your attention to this key, which shows you such things as atomic number. And the data chart. And again, for covalent compounds like phosphorus trichloride, those things are there as well as the polyatomic ions. And of course, we went over this yesterday. Now, here is where the energy stuff will be. Half-lives, radioactivity symbols. These are the energy equations, and these are where you can look up units. So for half-lives, here's the data, and what kind of stuff can we ask about it? Well, first of all, I want you to remember that half-lives, they're about clocks. They're our clocks in the universe. Uranium turns into lead. And when we take a zircon that crashed to Earth, and we grab that zircon, and if that zircon was formed when the solar system was, we can look at the amount of lead, compare it to the amount of uranium that it came from. With a half-life of 4.5 billion years, we can determine the age of the Earth. That isn't precisely how it was done. That's how we know the age of the Earth. Carbon-14 has a much shorter half-life, about 5,700 years. Carbon-14, which is radioactive and is constantly made in our upper atmosphere, turns into something else. Most of the carbon is carbon-12. If we compare the amount of carbon-14, which slowly disappears, to the amount of carbon-12 in, say, a sample of wood that was in a campfire, then we can tell the age of the campfire. And this is how, for example, we date the age of first settlement of North America by peoples from Asia. So the half-life works like this. Regardless of what it is, if you have a sample that's radioactive and it weighs 100 grams, one half-life later, there's 50 grams left. Two half-lives later, 25 grams are left, and so on, 12 and a half. Now, it turns out that it doesn't matter how much you have, but after one half-life, you have half as much. For carbon-14, it's 5,730 years. Here's how I know. It says it right there. Okay, so after two half-lives, if you have 100 grams and it became 25, you know that two half-lives have gone by, which means that's 11,460 years. You can run this in both directions. What I mean by that is, if you know something has gone through 3 half-lives, that's 17,000 years. If you know it's carbon's half-life and it's 17,000 years old, you know that it's gone through 3 half-lives. Well, on to nuclear equations. Here we go. So, see what's here, energy equations. See what's here and what is not here. Okay, there's no E equals H nu, there's no E equals MC squared. It's potential energy, it's kinetic energy, mechanical energy is defined there for you. Having trouble focusing. And heat energy. Energy is the mass times the heat capacity times the change in temperature. These are the equations, and there will be at least one of each on the test. If you can't remember that energy has joules, you might want to know that. Here it is here for you. Time in seconds, distance, mass in the kilograms, distance in meters, etc. like that. Now, so radioactivity symbols. 3 kinds of decay were first discovered in order. Alpha, which is really a helium nucleus. And I want you to see alpha particles. They're quite heavy compared to these other ones, but they get stopped at paper. Beta is an electron, and it can make it through paper but get stopped at aluminum. Gamma is really a high energy light ray. It can go through paper, it can go right through aluminum. It takes lead to stop that. Now, nuclear equations, law of conservation of mass here. If you have carbon with 6 protons and 14 particles in the nucleus, and it turns into another element, these numbers still have to add up. What I mean is that these two here have numbers and they have to add up to 6. What plus 7 is 6? -1. What plus 14 is 14? 0. Oh! Happy face is an electron. Here's another one. Uranium 238 spits out a beta particle. Helium, right? Helium's a beta particle. Beta. There we go. Okay, so anyway, and it makes something else. Well, what is it? Well, whatever this number is, when you add 2 to it, it's got to be 92. 92. So there's our uranium. There's my fat finger. There's uranium. Something plus 2 is 92. Oh, it's thorium. Look, it's thorium. Okay, so whatever number is up here plus 4 has to be equal to 238. So it's thorium 234. That's it for energy equations. Finally, nuclear energy. Here is the really quick version. It's going on in the sun. That's fusion, when things join together. Hydrogen plus hydrogen make helium and a bunch of energy. It's also used in nuclear weapons, modern, if you can call it that. The H-bomb, the hydrogen bomb, it's the same thing. We don't know how to control it. So because we can't control it, there's no commercial power stations, not yet anyway. A whole bunch of above ground testing was done in the 50s and 60s, and it left radiation in the atmosphere. So radiation levels were higher then than they are now. And they're higher in me, because I came along right there. In my teeth, we would be able to detect a little bit of extra radiation. Thanks, weapons industry. Okay, fission. Splitting apart, for example, U-235 will break apart into some more matter and energy. In early nuclear weapons, fission was used. Hiroshima, Nagasaki, there. All commercial nuclear power stations use fission. Good ones don't melt down. Chernobyl did, and Fukushima you will know about. These are more recent, though. Yeah. Okay, that's energy. Something we haven't mentioned for a little while is the Hertzsprung-Russell diagram in astronomy. Okay, so here's just a reminder about it. So here's the thing. If you look up in the sky and you look at every star and you say, I'm going to rearrange them on a graph. I'm going to take all the brightest stars and put them higher on the graph. I'm going to put all the blue stars on the left and the red stars on the right. What happens is 90% of the stars that we see in the sky end up on this diagonal. This diagonal is called the main sequence. 90% of stars are here because 90% of stars are burning hydrogen, as is our star at the moment. And so that puts them here. The bigger ones are bluer and also brighter. White is a little less blue and a little less bright. Yellow's in the middle, and then red here. So our sun will run out of fuel in about in about another 5 billion years, and it will run out of hydrogen fuel and start burning helium, and it will turn into a red giant. This will be our sun in 5 billion years. Then it will, the nuclear reactions will slow down. In fact, they will stop. Much of the outer atmosphere of the sun will dissipate into space, and what will be left will be a hot white core But because it will be very small, it will be right here. White dwarfs are the remnants of red giants that didn't explode. Hot white, and it will just be there for 100 billion years and then cool off. Supergiants, they're the ones that will explode and either go into a neutron star or a black hole. Wow. Okay, everybody. Well, I hope that wasn't too dreadful. Good luck on your exam. I'll be in next week and later this week, hopefully. And if you need to see me, and also you can email me. Okay, well, good luck and thanks.